Hello and welcome back to another High Peak Education video. In this video, I would like to address the idea of circular motion, centripetal acceleration, centripetal force, and in general, what does it mean for motion when an object starts to turn, namely to change its vector direction heading. I will use several examples, several simulations, and several instances to explain this concept. Many times in most physics textbooks, centripetal acceleration and centripetal force are dealt with in kinematics and in Newton's laws, that is the forces chapter, but then they are neglected for many days, many weeks, until we start discussing solid body rotation, that is, the rotation of an entire solid object, many particles put together. I will first address what it means for centripetal acceleration and centripetal force on a particle, but then I will show how it is really very similar to solid body rotation, the rotation of an entire solid object, because an entire solid object that is rotating is really just a large collection of particles. So, let's start off with this simple thought experiment. Suppose we have a ladybug that is able to move anywhere in the plane. That is, this ladybug is able to move freely in the x direction, the y direction, horizontally or vertically. We will exclude ourselves, by the way, in this video and in this discussion to rotation in a plane and motion in two dimensions. In general, you could imagine that rotation could even be three-dimensional. I mean, it is very possible to have something rotating like this and then change its axis of rotation. But we will not really address that in this video. But you could imagine more complicated cases like maybe a whirlpool or a tornado where the axis maybe tilts over, but that's beyond the scope of this discussion. So, imagine this ladybug is resting in the plane, and we can show the ladybug's motion with one of two types of vectors, and in fact, very soon I'll actually be showing both. So, what I'm going to show is I'm going to show the ladybug on a certain path, and that's her velocity vector. I can control it. Notice the velocity vector will have a certain length, and it's going to be in color green, and the longer the velocity vector, the larger the ladybug's speed. So, the faster she goes, the longer the length of the velocity vector. How about her acceleration vector? Well, if she's moving to the left and accelerating, her acceleration vector is to the left. And if she's slowing down but still moving to the left, her acceleration vector was to the right. And notice that the acceleration vector was kind of in that sort of peach color. Let's also note that whether we're showing the velocity vector or the acceleration vector, either way, that this entire time I want to track her motion, that is her path, by showing these dots. And these dots are reflective of where she has been, so she leaves a trail of dots, but then also notice when the dots are close together, her speed is generally small, and when the dots are further apart, her speed is faster, and that's because she's covering a greater amount of distance in the same amount of time. What I would like to do is I would like to return her. Here's an acceleration. Notice the acceleration now is backwards. I'd like to return her to sort of the lower left portion of this figure, and then I'd like to clear. Okay, so I'd like to start a bit of new motion, and I'm actually going to show both vectors at the same time. If you recall, earlier in Calculus-Based Physics 1, there's a discussion on when the acceleration and the velocity vector are in the same direction, she is speeding up. When the acceleration and the velocity vector are in opposite directions, like you just saw there, she's slowing down. Now, if we're moving to the right and both acceleration and velocity are in the positive x direction, we speed up. If we're moving left and both the acceleration and the velocity vector are left, that's in the negative x direction, we're also speeding up, but we're speeding up towards the left. Both the velocity and acceleration have the same sign. That is, they're both a negative velocity and a negative acceleration. Imagine the x direction, by the way, is defined to the right, the positive x direction. Okay. Now let me go ahead and clear and pause, and then now I want to show something that we haven't really discussed yet in this class, or at least for my class, and I want you to certainly be aware of. Imagine the ladybug is not only in linear motion. Imagine the ladybug starts to make a turn. Imagine the ladybug changes her vector velocity direction. So let's see what that looks like. So let's start the motion, constant velocity roughly, and then all of a sudden, suppose she takes a turn. Do you notice that? Notice that the ladybug is actually taking a turn, and there seems to be an acceleration that is no longer directed in the direction of her motion. There seems to be some acceleration that's directed sort of towards the center of the curve. Hopefully you can kind of see that. Now notice, if she makes a really tight turn, that is a very small radius of curvature, you might say. Then there's a large sudden acceleration towards the center of the curve. If she makes a very wide turn, there's not that much acceleration towards the center of that curve. So again, sharp turn, large acceleration, and if she makes a wide turn, not so much acceleration towards the center. Okay? Notice that acceleration is always towards the center of the curve, not outward from the center of the curve. Okay? Also notice that if she makes the same size curve slowly, the acceleration is kind of small. But if she makes that same size curve but just goes faster, it seems that the acceleration is greater. So these are a couple observations we can make. So in fact, let me actually show what linear motion looks like for her. So that's linear motion. So remember, linear motion, which is constant velocity, constant direction, and zero acceleration, we know what that looks like. We know what the dot should look like. But what should circular motion look like? Notice circular motion, in fact uniform circular motion, is going to be a very specific path. Notice her path is in a circle. The spacing distance between the dots is uniform. Notice the length of her velocity vector stays the same. The length is reflective of her speed. Notice that her speed is constant. But notice her acceleration is not a constant. In fact, it's always changing direction. And notice even her velocity vector is not a constant. Now you may say, wait a minute, that looks constant. It's not constant vector. It's a constant speed, it's constant magnitude, but it's not a constant direction. In fact, the direction is always changing. And notice the velocity vector is always tangent to the path of her motion. Okay? This is what we call uniform circular motion. Circular motion at a constant speed. Okay. In fact, let's change the circular motion to another bit of motion that is rotational, but is not uniform circular motion. Let's change to this one. And notice now we take another special shape, which is not a circle, but is actually an ellipse. And notice the velocity vector is always tangent to the path. In fact, by the way, that's one of the ways you actually define motion itself. A velocity vector will always be perpendicular to the position vector. That is, if you imagine some origin here and pause and draw a position vector from that origin to the ladybug, the velocity vector will always be perpendicular to that direction, that position vector. In fact, it will always be it will always be tangent to the path that the object is moving on. Okay? And notice the acceleration vector. When we were in circular motion, the acceleration vector was always perpendicular to the velocity vector and in the opposite direction of the position vector. But now notice that if we go back to an ellipse, so again, here we have an elliptical path, the acceleration vector is always towards the center of the curve, not necessarily the center of the ellipse per se, but the acceleration vector and the velocity vector are not necessarily always perfectly perpendicular to one another, but notice when the object is changing its speed, say like speeding up, the acceleration vector is in the some more so same direction as the velocity vector. And when the object is slowing down, the acceleration vector is in the opposite direction of the velocity vector. And then say right there, so right there, the acceleration vector and the velocity vector are roughly perpendicular. So this we call non-uniform circular motion, but non-uniform circular motion is such that it's rotational motion that is non-uniform. In other words, it's not a circle, and the speed and the velocity direction are constantly changing, and the acceleration direction and magnitude are constantly changing, but at least we're staying on the same path. So this is what we mean by elliptical motion. Now, by the way, there is also such a thing as non-uniform circular motion. In other words, circular motion not at a constant speed. So I'll address that here in just a moment. Notice, picking up from where we left off, let's be a little more mathematical. Let's be a little more specific. Let's be a little more quantitative about this particle that is changing its direction. And let's in fact only examine for now the uniform circular motion case. That is, circular motion at a constant speed. So imagine that we have here an x-axis to the right and a y-axis upward. Again, we're going to restrict our motion only to the plane. Also note that the position vector is in red and that the particle is just some dot that we're going to track along. And what we can do is we can also look at the x and y component as it goes along. Now, the focus of this video will not be the x and y components. In fact, when this thing starts in uniform circular motion, you'll notice that the position started at a maximum for x, okay? And you'll also note that the position in y started at 0, okay? And that's because you could imagine the x component here is going to mimic a cosine t function, and then the y component is going to mimic a sine t function. Now, by the way, technically, depending upon the rate of rotation, it's going to be more like cosine omega t and sine omega t, where omega is going to give us some rate of rotation, but that's beyond the scope of what I want to look at. Notice that there is certainly a relationship between uniform circular motion and the oscillation, if you will, or the periodic motion in the x direction and the periodic motion in the y direction. But that's beyond the scope of this video. I will save that in physics for a later time. So for now, I'll try to do my best to kind of gray this out. All right, so let's just focus only on this uniform circular motion at a constant speed. Okay? Notice that the position vector from the origin remains at a constant magnitude, that is, a constant radius. And also notice that the rate of rotation is constant. Okay? Note that I can change the rate of rotation, but let's examine the position, the velocity, and the acceleration, and the force for this constant rate of rotation. Okay? Also note that the radius is staying fixed in terms of its magnitude. Okay, so let's in fact pause for now. And then now I want to ask you, what do you think the velocity vector direction should be? Okay, so hopefully you had a chance to pause there. And the velocity vector direction should always be tangent to the path. So it should always be tangent to the circle. And so when this particle is moving around in uniform circular motion, the velocity vector is always tangent to the path. Notice the speed is staying constant. That is to say, it's constant velocity vector of magnitude. The direction is constantly changing, but notice that it's changing at sort of a nice uniform rate. I mean, it's sort of oscillating, as we said before, in terms of its x and y components. But it's always tangent to the path, and the path is this circle. How about if I pause again and ask what is the direction of the acceleration? Hopefully you had a chance to pause and think about that. It should be directed towards the center of the circle. In other words, we give this a term, and as long as it's uniform circular motion only, the entire acceleration vector is centripetal acceleration. Think about the word centripetal. It sounds like center trip or center seeking. Centripetal acceleration causes the object to accelerate towards the center, and it's always accelerating towards the center of the circle because the object is constantly turning. It's constantly changing direction only, not speed. Now, you can hopefully recall Newton's second law of motion. And we know that when we have an acceleration, we have a force, namely a net force. And that net force we're going to call the centripetal force. Now notice if we take this centripetal acceleration and just multiply by mass, we get the net force, which is the centripetal force. And this centripetal force is only different from the centripetal acceleration in that it's scaled up by a constant. In fact, if I pause and change the mass instead of 1 kilogram to 2 kilograms, so I think I need to reset. Let me change it to 2 kilograms. Notice that the scale would change. Okay? So the scale would change, but notice that what would be different is really nothing about the direction here. Let me reset and try to change to a slightly different mass. So maybe 2.5. Notice that if I change to 2.5, indeed, the scale of the force down here is staying the same, but the vector is looking longer. And that's because the centripetal acceleration is the same, what it was before, but now the centripetal force is just scaled up by the mass. And scaled up by the mass is just saying that force and acceleration are really the same thing. They're really the same direction as far as their vectors, except we multiply by mass, and mass is a constant. So the centripetal force is greater when the centripetal acceleration is greater. But the centripetal force is greater when the mass is also greater. Okay. Now note, let's go ahead and go back to our position example. So here's what we mean by uniform circular motion. Okay. And what I'm going to do is I'm going to change, I'm going to change the period. I'm going to make the period in some sense smaller. So I'm going to make this a shorter period. Now period is the time it takes for one rotation. Previously it was taking 5 seconds to make one rotation. Now it's only going to be 2 seconds. So indeed I think that not only will we have a greater rate of rotation, but I also think that the velocity should be larger because we should be moving faster. We should be covering the same distance in less time. And I think that the acceleration is going to be greater because we're going to require a larger acceleration to cause us to turn that fast velocity in towards the center more rapidly. So notice now we're going to have a larger rate of rotation. So that is what we see. So the period is now only 2 seconds for this thing to make one full rotation. Let's look at the velocity vector. Okay. Notice the velocity vector is faster for sure. And indeed also the acceleration vector is quite a bit larger. The centripetal acceleration is quite a bit larger. And again, it's still directed inward towards the center. Okay. All right. So this is what we mean by uniform circular motion of a particle in a situation where the path is only a circle. That's uniform circular motion by definition. Now, by the way, let's go back to that more comfortable 5 seconds for the period. So you remember, this is what the rate of rotation looked like. Okay, and let me reset. But now let me change the radius. Let me make this particle out to be a larger radius. So let's increase the radius to doubling, namely, let's see, 4 meters as opposed to 2 meters. And notice the object is going to have also a different centripetal acceleration. And it's also going to have a different velocity. And the position is going to be different. So now let's be a little more quantitative that we haven't been thus far. Okay? So our original case, notice that the position was started at 2 meters because that was its original radius. And notice x starts at 2. And as we let this go along, then y goes up to 2, then goes down to 0, then goes down to -2, comes back to 0, and so on. Notice this happens with the x and y component throughout. Notice the velocity is going to be 2.51 meters per second. And notice that the x and y velocities will change from positive 2.51 meters per second to 0 to negative 2.51 and hit all values in between. Notice at any point, say down here in quadrant 4, the x velocity could be positive and the y velocity is positive. But then notice that in quadrant 1, the x velocity is negative and the y velocity is positive. And notice that those just cycle through in as sort of those periodic waves, which again, we're not really focusing on here. But notice that the magnitude of the speed stays constant, but then also what's staying constant is what we call the angular velocity. Now the angular velocity is given the symbol omega, and notice that it's in units of radians per second. Notice it's 1.26 radians per second in this case. And that's because if we know the linear velocity and we divide by the radius, so if I take 2.51 and divide by 2, that's meters, that's the radius, I should get the angular velocity of 1.26 radians per second. By the way, this should actually be closer to 2.52. It's probably some rounding issue here, and then divide by 2, you should get exactly that. Okay, so the angular velocity is constant as well, not just the linear velocity. I'll discuss that more as we go along here. And let's now do the acceleration. Now notice the acceleration has a value of 3.16 meters per second squared. Again, notice that the x and y components of the acceleration at any point, suppose I try to stop near the top of the circle, the acceleration is negative in the y direction, and the x direction it was meant to be really close to 0. Let's see if I can cleverly stop near the top. Pretty close, but the x acceleration's pretty close to 0. Notice if we pause near the left-hand side of the circle, the x acceleration is positive, the y acceleration is pretty close to 0. And then, of course, it's everywhere in between, because the magnitude is, again, 3.16 meters per second squared. The direction is given by these axes. Now, you may ask, how did you get 3.16 meters per second squared? Okay, so if I take that velocity, which was, we can go back to it, I don't remember it offhand, 2.15 meters per second, and if I square that, and then divide by 2, so 2.5 squared is roughly 6.3 or so. And then I divide that by 2, that's the radius, I should get a centripetal acceleration, which is 3.16 meters per second squared. So that's like v squared over r. Okay? So the faster we go, the larger the centripetal acceleration, and the larger the radius, the smaller the centripetal acceleration. Okay? Notice if I take 3.16 meters per second and multiply by 2.50 kilograms, that should give us the centripetal force. So that's 7.90 newtons. Remember, the centripetal force is in the exact same direction as the centripetal acceleration, but it's just literally scaled up by the mass. Larger mass, larger centripetal force, but certainly larger centripetal acceleration, larger centripetal force. Okay, now let's take one more step and say, what if we were to go back to position, but now let's make the period exactly half as much, so 2.5 seconds. Okay, notice nothing about the position changes, it's just that we rotate through at a faster rate of rotation. It only takes 2.5 seconds in order to complete one full rotation. Okay? Notice the velocity, though, is now scaled up by a factor of 2. It's twice as much as it was before, and that should hopefully make sense to you, because since the period is half as much, we cover the same distance in half the time, so our speed has to be twice as fast. And that is indeed what we see for the tangential velocity. Okay? Notice also the angular velocity is twice as much, because again, we're covering angles, we're rotating through radians, which is a unitless angle measure, in the same amount of rotation, say 2 pi radians, but it only takes half as long. The time is half as long. Okay? So that's exactly what we mean by we doubled the linear velocity, which we call the tangential velocity, and we also double the angular velocity, which we call the rotational velocity. Okay? All right. So let's pause, and now let's go to acceleration. Notice the acceleration is quite a bit larger. In fact, it should be, if you double the velocity, it should be 4 times as much. Okay? So now it's 12.6 meters per second squared. Because again, that's v squared divided by r. Okay? Now, what happens to the force, namely the centripetal force? Well, if we just take this centripetal acceleration and we multiply it by the mass of 2.5, we've got 31.6 newtons. And again, since the centripetal acceleration has gone up by a factor of 4, so has the centripetal force. But again, we multiply by mass. Okay, so one thing to say here is the following. Okay, that the radius also has an effect on all these. So let's go back to our basis case. Let's reset, and let's go back to 5 seconds. And let's also go back to position. Now, what if the radius is twice as much? Well, the x and y magnitudes will be twice as much, because we're twice as far away from the origin. Notice that twice as far away from the origin, being radius, this lends itself to polar coordinates. Hopefully you understand what I mean by that. That x and y might not be the best coordinates to use here. R and theta, radius and angle, r in meters and theta in radians might be the best coordinate system here. I'll discuss that at a later time. Then let's also say what happens to the velocity. Well, if the radius is twice as much, notice that the angular velocity is the same as our basis case, 1.26 radians per second. But the velocity that's linear velocity, that is the tangential velocity, is twice as much as it was before. If you have twice the radius, then we know the circumference of the circle goes by the formula 2 pi r. If r is double, the circumference is double. But if the rate of rotation is the same, then, in other words, we also have to, in 5 seconds as before, the period is the same, go through the same 2 pi radians, the same number of angles, then we have to cover twice as much distance in the same time. So the speed has to be twice as much. So the tangential velocity is proportional to the radius. If you double the radius, you get double the linear, or the tangential velocity. Okay? Now, let's also have a look at the centripetal acceleration. Now, the centripetal acceleration is going to be v squared over r. Notice, interestingly, the centripetal acceleration is twice as much as the basis case. Why is that? Well, it turns out the velocity went up by a factor of 2. So a factor of 2 squared is 4 in the numerator. But since the radius went up by a factor of 2, that's a factor of 2 downstairs in a denominator. So 4 over 2 is a factor of 2. Another way to write centripetal acceleration is omega squared times r. That is the rate of rotation, the angular velocity, squared times r. Since r just went up by double, it should be double the centripetal acceleration. Okay, so I hope that makes sense to you. Okay, so this is more quantitatively, at least trying to get our head around how uniform circular motion works and how these variables are related to each other. Of course, if the centripetal acceleration is twice, we already know the centripetal force should be twice, but again, to get the centripetal force as 15.8 newtons, we take the centripetal acceleration magnitude of 6.32 meters per second squared, and we multiply by the mass of 2.50 kilograms here. Now what I have here is yet another example of a particle that is going to experience centripetal acceleration and thus centripetal force. What I'd like to do is I'd like to first have the particle move with a constant speed throughout this path, and let this path be this orange sort of brown color, and the velocity vector will be shown to you as well as the acceleration vector. Okay? Now at first, because the speed is going to be constant, there will only be centripetal acceleration. By the way, centripetal acceleration is sometimes called radial acceleration, because radial acceleration is just directed in the opposite direction of a radius. Imagine that there was like some sort of imaginary circle here roughly hugging this curve. So radial acceleration, if you define sort of a radial axis, then, that would be the direction of the acceleration. Okay? So we're only going to see radial acceleration first. That should be the same thing as the total or the net acceleration. Okay? So let's go ahead and watch. Notice that as this thing rounds the bend, the radial acceleration is directed towards the center of an imaginary circle here. That's the centripetal acceleration. When the object's in linear motion or straight line motion, which we saw earlier in the semester, there is no radial acceleration. Okay? The radial acceleration is very, very small. Now notice when we round this wider turn, the radial acceleration went up. It's towards the center of this much larger circle. So since the radius is larger, the radial or the centripetal accelerations like generally less for the same speed. Let's repeat the same experiment but with double the speed. Notice that if you have double the speed, you should have, for the same radius as we had before, double the centripetal acceleration. And that's because v squared over r, if v is doubled, I'm sorry, I should actually say it should be 4 times the radial acceleration. Because if v squared, if you double the speed, you get 4 times the centripetal acceleration. So what you'll see is you'll see much larger centripetal accelerations toward the center of this circle imaginary, this circle imaginary. Imagine there being some sort of circle sort of tangent to these curves. And then you'll also see the object go through this path much more quickly because we're moving at 3 meters per second instead. Okay, so notice now the centripetal acceleration is greatest when the curvature is greatest. Notice when the object's in linear motion, the centripetal or the radial acceleration is very small. And notice the radial acceleration is biggest where we're really turning, but it's really small when the object is moving roughly in linear motion. Okay, now let's go to the situation where we have 1.5 meters per second for the initial speed, but let's give the object a tangential acceleration. Now notice, the object has tangential acceleration and centripetal acceleration. And the total acceleration is going to be given by the thicker purple vector, the darker purple vector, whereas the 2 light purple vectors are the centripetal and the tangential. That is, the radial and the linear along the path accelerations are both shown. So let's go ahead and start this up. Okay, and when we start this up, you'll see, first of all, the object is just going to move faster and faster as it goes through this path. Why? Because we're accelerating it the whole time in terms of its speed acceleration. Tangential acceleration is speed acceleration. Centripetal acceleration is direction acceleration. In other words, you could imagine that the radial acceleration is reflective of how much the object changes its vector direction, and the tangential acceleration is how much the object changes its vector velocity length. Okay, so you'll also see that the centripetal acceleration will certainly be larger than it was before in the basis case of just moving at a constant 1.5 meters per second through these curves, because as we go progressively faster and faster, if you have v squared over r, v is getting larger, so the centripetal acceleration is also getting larger. So look at that. The centripetal acceleration is larger than it was before. The tangential acceleration is causing the thing to move faster, and the centripetal acceleration was quite a bit larger here than it was. By the way, we call this type of motion non-uniform motion. Non-uniform being, certainly it's non-uniform circular motion, because we're not moving just in a circular path, nor are we moving in a circular path in a at a constant speed, or for that matter, a constant rate of rotation anymore. As soon as there's a tangential acceleration, you have non-uniform motion. Okay? And in fact, things get a little wild if you make the initial velocity 3 meters per second. Notice, as soon as we made the initial velocity 3 meters per second, instantly the centripetal, which is the radial acceleration, was larger. Notice this total acceleration is the vector sum of the centripetal and the tangential acceleration. That is the radial and the linear accelerations of the object. You perform a vector sum where you add vectors head of this vector to the tail of this vector. You get this total acceleration vector. And you'll see that the object has quite large centripetal accelerations towards the center of these curves. And it's even larger than the last case. Now what I have here is another example of where we can examine uniform circular motion for objects that are multiple objects on a turntable. Now for this turntable, you could imagine this is maybe like a record or a CD or a DVD or maybe even a hard drive. It probably depends upon how long you've been on Earth. So what I will do is I will be able to click and put particles on this turntable that are reflective of different colors. And you'll notice that when I click on them, you'll get a sense of what their rotational speed is versus their tangential speed. And then I'll also be able to control the rate of rotation, and the rate of rotation can be controlled here. Okay, so I can make the rotational speed of the entire thing faster or slower. But this whole thing is going to move clockwise in this case. Now, by the way, one thing I did not say before that I could have said is, so one thing I should have mentioned before is, notice you may ask, why does this particle move counterclockwise? Well, that's because when you push x into y, you could imagine x pushed into y by the curling of your fingers of your right hand, some axis direction, namely you might call that the z-axis, the positive vertical axis, which goes out of the plane of the piece of paper, is positive by orientation if you use the right-hand rule. In other words, if x is rotated into y in the y direction, counterclockwise, then we can define counterclockwise as the positive direction, as a positive right-hand corkscrew. In fact, 99% of coordinate systems in this world, even if x is not necessarily to the right and y is upward, x pushed into y, so in other words, the right-hand corkscrew, is going to give the positive direction of vertical, the third dimension of an axis. So, by convention, we retain that counterclockwise is positive and clockwise is negative for the vector sign of the angular velocity, that is omega. By the way, those of you over in Europe, I know that you would call counterclockwise, you would call that anti-clockwise. So I just want to be sensitive to my multiple views. So what I now have here is a turntable, which is going to be another example of uniform circular motion. Also note that with this turntable, I can click and put several different particles on this turntable, and we'll see how the tangential speed is going to be different for each of them, but the angular speed will be the same for them. Also note that we'll see how tangential speed depends upon the distance from the center, that is the radius, and we'll also see if I change the angular velocity, that is the rate of rotation, how the tangential speed and how the rotation looks different. By the way, this entire turntable rotating is what we call solid body rotation. And a solid body is just an entire solid body, the entire thing rotates about an axis. And notice that a solid body rotation is just the same thing as a collection of many particles. Okay, one more thing. As I already mentioned previously in this video, this is actually the negative direction for omega. That is, it's clockwise. But we're not going to really worry about that. I only really want to focus on magnitudes for this experiment. That is, the magnitude of the tangential speed, the magnitude of the tangential velocity, etc. So let's imagine we click somewhere middle of about this turntable. Okay? And what we should see is we should see a certain angular velocity and tangential velocity. Okay? So look at that blue dot. Notice that right about where I clicked, you'll see that the blue dot has a certain tangential velocity. That's how fast it's moving in meters per second. And it has a certain angular velocity. That's how quickly it's rotating through angles. That's in radians per second. If I click again, where at the same radius as this blue dot, you should see another blue dot that has the same angular velocity, but and its tangential velocity is also the same. But these two objects are just at different positions. So they experience very similar outcomes in life. It's just that their instantaneous position is different. Because if I were to pause this, you could imagine that the position vector out to each of these is just a different radius vector because each is just at a different location. Okay, fine. Now let's do something a little more interesting. Let's see if we can set up a particle that's at a larger radius than the blue dots. That is to say, we want to keep the angular velocity the same, but we want to increase the radius. Now, we investigated this earlier, but let's see if I can demonstrate this to you, that if the radius increases, we should expect the tangential velocity to be greater, but not the angular velocity, because the rate of rotation is the same, but the radius is larger, so we have to cover a greater distance in the same time. Look at that. Now we have a purple dot. It has the same angular velocity as the other two dots. I think it has the same period. It takes the same amount of time to make one full rotation. So its angular velocity, sweeping out radians per each second, is the same as the other two. But clearly, it's moving faster. But what do we mean by faster? Not faster in terms of rate of rotation, in terms of angular velocity, but faster in terms of linear velocity or tangential velocity magnitude. And that's because it's moving a larger distance in the same time, because the circumference is greater when the radius is greater. Now, I know you're on the edge of your seat, but I should be able to do the same experiment if I click at a radius that's smaller than both purple and blue. That is, the tangential velocity should be smaller, but the angular velocity of all of them should be the same. So let's see if we can confirm. Look at the green dot. Now the green dot is at a smaller radius, and it has a smaller tangential velocity magnitude, a smaller speed. Do you notice that if I was to do this for many radii, you would have this nice linear profile where the tangential velocity increases with radius, but they all have the same angular velocity. In fact, as a proof, let me increase the magnitude of the angular velocity. Let me increase the rate of rotation, and you should see all of these objects increase their tangential velocity, but all at the same rate. Okay, look at that. We still have a linear line between green, blue, and purple, but since the rate of rotation is now greater, they all have a greater tangential velocity. If the rate of rotation is double, then they all have twice the tangential velocity they had. But now they all have a greater angular velocity. So you might say this is a greater RPMs, revolutions per minute. That's also a very common unit for angular velocity, but that's not the SI unit. The SI unit is radians per second. But revolutions per minute is a very common unit as well. So what we have here now is a turntable with two particles, namely a ladybug and a beetle. And this ladybug and a beetle have a different initial position. You can imagine this would be the position vector from the origin for each of these objects. Also note that they're going to be on a turntable so that their angular velocity will always be the same. In fact, all points on this turntable will have the same angular velocity. Now I'm going to try to rotate this turntable in the positive direction, which is counterclockwise. So that's the idea. And then furthermore, one of the things you'll see is the difference in tangential velocity and the difference in centripetal acceleration for the objects. Okay, so let's see if we can show that. Look at this. Notice that the object with the smaller radius has a smaller tangential velocity, okay, and the object with the larger radius has a larger tangential velocity and also has a larger centripetal acceleration. Okay? By the way, you should also note that the radius is about double for the beetle as opposed to the ladybug, so you have about twice the tangential velocity and twice the centripetal acceleration. Okay? So hopefully that makes sense. Now what I want to do, since these are both rotating, is I want to produce momentarily non-uniform circular motion. I want to increase the rate of rotation so that you'll see these acceleration vectors will no longer be straight towards the center, and you'll also see the velocity vectors change. Did you see that momentarily? Look at that. Now that it's moving faster, it's very hard to look at because they both have very large centripetal accelerations. And the velocity vectors are also quite large. Let's go ahead and see if I can slow this rate of rotation down. So let's try this again. But watch during the period of time when I speed this rate of rotation up. You'll see the tangential velocity is always tangential, but it's growing in size. But you'll also see that the centripetal acceleration is not the only acceleration. You also have a tangential acceleration. Did you see that? Watch it one more time. Hopefully you saw during the period of time when I was speeding this up that the acceleration was not only centripetal, but it ended up being having a tangential component. Let me see if I can slow this down and give it a tangential component. So look at that. I slowed it down suddenly. The tangential component was exactly in the opposite direction. To just show a few more examples, let's take a look at what solid body rotation really is. Imagine we have a turntable which is very funny shaped. I mean, basically, suppose it's this sort of grayish outline. And suppose we mount it here through some point of interest. This is going to be the axis of rotation. Typically, we define the x and the y-axis from there, but we also define the radius out to some point of interest and the angle theta. So that's going to be an angle theta in radians. Notice that we can still convert from radians to degrees, but radians in some sense are unitless. And by the way, let's go ahead and start this up. Notice that the radius stays constant, the tangential velocity remains at a constant speed, but notice that the angle theta will increase as we go around in radians. But notice every time we complete a full rotation, in some sense we start over with another rotation. Now notice, the reason that's important is because a lot of times you'll hear physics professors and other people talking about rotation say radians don't really exist or they're unitless. I like to preserve radians in terms of my discussions of rotation, but keep in mind, radians are only a counting unit because the total displacement of one full rotation is by definition 0, because we don't change our location in the universe if we go from the same position to the final ending position after one rotation. So radians are the unitless angle counting number that we retain. Notice that if we reset and I increase the angular speed to double, the period should be half as much. So we just rotate through twice as fast, but again, each rotation is one revolution, and in some sense it's unitless in terms of the total position change. You may ask the question, why is it centripetal acceleration and not centrifugal acceleration, or sometimes called centrifugal, sort of mispronounced? Now, the real force is always going to be centripetal, center-seeking. That is to say, the centripetal force is not a new way to have a force. It's not like the other forces, like tension or gravity force or normal force or friction force or anything like that. It's a new way to manifest the net force. In other words, some other force that has already been studied in a calculus-based physics 1 class has to manifest itself as the centripetal force. The centripetal force is only there to cause the object to turn, to change its vector direction. The centripetal force does not change the object's speed. That's going to be a tangential force, and that's forces that have been studied earlier in this physics 1 calculus-based course. So as a proof that the centripetal force is not a real force in the sense of it's not a different kind of force, it's just a new way to call the net force. What I have here is I'm imagining that if I spin a ball in a horizontal circle above my head, and that ball is attached to a string, and a string is going to manifest a tension force. Now that tension force should be towards the center, because that's holding us in towards the center. In fact, I can feel the ball pulling outward on my hand, but by Newton's third law, the tension force pulls the ball inward towards the hand. So the outward tension I feel is balanced by the inward tension that's on the ball, by Newton's third law. In fact, if you were riding on the ball, like if you imagine you were some ant or some ladybug, like we did earlier, riding on the ball, the faster you would spin, you'd feel sort of an outward force. But that's because our brains are used to thinking about our brains being in a resting reference state. Just like if you're a passenger in the car and the driver takes a sharp left turn, and suppose we're in the United States, so the driver's on the left and the passenger's on the right. So when the driver takes a sharp left turn, what actually happened is there's a centripetal force, that the friction held the car in towards the center to make that sharp left turn. But you think that there's an outward force on you. That is, you think there's a centrifugal force pushing you out towards the door to have your shoulder collide against the door. But that's only because you think that you're an inertial reference frame. Your brain thinks that you should always be moving at a constant rate. Okay? So what the real force, the object that's in circular motion, is the centripetal force. So by Newton's first law, if we break away the tension force, we should no longer have any net force. We should no longer have this center-seeking net force of the centripetal force. So what that means is Newton's first law of inertia should take over, and the object should follow the direction of its tangential velocity. In other words, the velocity should take this object tangent to the circle, because the tangential velocity is always tangent to the circle in uniform circular motion. So let's try to break the string at the top of the circle. And look at that. The velocity is exactly perpendicular to the radius. This object flies off in a path that is perpendicular to the radius because the tangential velocity is perpendicular to the radius in uniform circular motion. We know from Newton's first law that an object in motion will stay in motion in a straight line unless acted upon by a net outside or an external force. As soon as the net force goes away, which is the centripetal force, but remember the centripetal force is just what we call the net force, so as long as the tension goes away, then the object suddenly is overtaken by Newton's first law, so it has linear motion at constant velocity in the direction that it was already going with its tangential velocity. Let's look at one final example of non-uniform circular motion. And it turns out non-uniform circular motion can be shown when an object's in a vertical circle. In other words, if gravity is at play vertically. So what we have here is we have a person on a swing set, on a swing. And let's model this person as a particle. Let's ignore the mass of the chain and let's model this person as if they're a ball and look at their free body diagram. Notice that mg, that is the weight force vector, can be decomposed into mg cosine theta and mg sine theta, where theta is this angle. It's this angle with reference to straight down vertical. Now, notice that mg sine theta is very similar to what we've seen earlier in the semester in this course. Mg sine theta is the component of the weight that would bring an object down an inclined plane. In the same way, mg sine theta is the component of weight that would bring a ball on a string down towards the center. In fact, this we call the net restoring force for a pendulum. We'll talk about a pendulum a lot more later this semester, but suffice it to say, it's the force that causes the mass to move down towards equilibrium. Whereas mg cosine theta is exactly what balances the tension force. Why? Because the tension force is going to change throughout this motion. In fact, I think the tension force is going to be greatest at the bottom because the tension will need to completely balance the weight. But when the object is at its highest point, the tension will be least. That's because cosine theta is a decreasing function of theta as theta goes from 0 to 90 degrees. So when we're at theta equals, I don't know, say 30 degrees here, cosine of 30 degrees is only square root of 3 over 2, and the sine of 30 degrees is 1/2. So sine is an increasing function of theta as theta goes from 0 to 90 degrees. And that means this force that brings us down towards equilibrium is greatest when we're maximally extended from the origin. So notice the entire force right now is going to be tangential force only. The radial force is going to be 0, but notice the radial force, which we know to be like the centripetal force, is going to constantly change because the person's speed is going to change and the radial force will change. By the way, I said 30 degrees, but the initial angle is actually set to negative 35 degrees. Okay, so let's set the person to negative 30 degrees to start. Get as close as we can. Okay, pretty close to negative 30 degrees. Okay, so notice that if the weight is 245 newtons, mg sine theta should be pretty close to half of that. So about 122.5 newtons. This is not exactly 30 degrees. But notice that, I mean, it's pretty close because this is negative 30.1 degrees. And then mg cosine theta should be, let's see, this multiplied by square root of 3 over 2, and then you should get this number. Okay. Notice that the tension force is always going to balance the mg cosine theta, which is the component of the weight that's anti-parallel to the tension. Okay, so let's let this person start. Notice how the forces change. Notice the weight never changes. That's because weight, in some sense, as long as you're in a gravitational field, is intrinsic to the object. We know mass is the most intrinsic thing to the object, really, because whether we were performing the swing on Earth or on the moon, you would still have the same mass. But as long as we assume the gravitational constant to be the same, the weight does not change here on Earth. Notice the tension is constantly changing, and it's constantly equal to the mg cosine theta. Okay? And that's because, so let me just pause somewhere here. So I'm actually saying that somewhat incorrectly, I guess. Anyway, I thought it should be the same. Maybe I can make a correction about that in the video. But in any case, the object has a tension force. It also has an mg cosine theta. And it also has an mg sine theta. But the mg sine theta is the same thing as the tangential force. So the tangential force is what causes this object to speed up and slow down. That's this mg sine theta. Notice when the object's moving upward, the tangential force is causing it to slow down. As the object moves upward to the left, the mg sine theta is decreasing the speed. When the object starts to come back downward, the tangential force increases the speed of the object. Okay? On the other side, if the mg sine theta is in the opposite direction of the instantaneous velocity, we slow down. If it's in the direction of the instantaneous velocity, we speed up. Okay. Now, let's see. The weight does not change, but mg sine theta and mg cosine theta constantly change throughout this thing's motion. So notice that we have the greatest centripetal force when we're at the bottom of the swing, and we have the least centripetal force when we're at the top of the swing. In fact, the centripetal force will be exactly 0 when we're stopped at the top of the swing, because the velocity is 0. Centripetal force is going to be mass times centripetal acceleration. So it's going to be mv squared over r. But if v is 0, then there's no centripetal force, thus no radial force. But notice the tension force is going to be greatest at the bottom, okay? And the tension force is actually going to be larger than the weight. Why is that? So I kind of misspoke earlier. And sorry for that. The tension force is equal to the weight plus the centripetal force. How do I know that? Because if the tension force is only equal to the weight, then the object would just be staying at put. But the tension force has to be larger than the weight because since the object's in some bit of circular motion, the tension force also gives us a net force, which is the directional force. So the tension force should not be the exact same as the mg cosine theta the entire time. Okay? So in fact, the tension force is always going to equal to the mg cosine theta plus the centripetal force at that moment. So that's correct. The tension force should equal mg cosine theta plus the centripetal force at that moment. So let's reset and let's see if we can investigate that. Let's say we go over on the right hand side. So let's stop right about there. Whoops, I'm sorry. Let's go ahead and pause, I should say, right about there. Notice at this moment, the radial force is 8.77 newtons. And that is the centripetal force. Notice the mg cosine theta plus the radial force, which is the centripetal force, should equal to the tension force. That is to say, the tension force is preventing the object from falling through the swing, but it's also causing the object to change direction. Then, you'll notice that when the object is at the bottom of the swing, the tension force is greatest, and that's because we're moving the fastest right there. So the tension force is, again, equal to mg cosine theta plus the radial, or the centripetal force. So, this is what we mean by non-uniform circular motion. Objects in vertical circles have net forces on them. The net force is given by the force that's causing it to be in circular motion, in this case the tension. But notice the tension sometimes has to balance another force, like mg, but then it also needs to be larger to allow for the centripetal force. Notice the tangential force is also there because that's what causes us to speed up and slow down. Okay, I hope this makes sense. I know this was kind of a long video and a lot to work through, but I hope this makes sense to you. Thank you very much for your attention. Please smash that like button if you like the content, and please subscribe to the channel to grow the channel. Please share this with people in your sphere of influence, and I will look forward to seeing you in the next video.